Hello guys, this is Joe East here. We're gonna today talk about the polarization index so you guys can quickly understand it first, and then we're gonna go and show you how to do a quick polarization index check with some Megger equipment, specifically the S1 568. Okay, polarization index, what are we doing here? If you look on a graph, we're measuring the difference between the resistance at the 1 minute point and the 10-minute point of any particular piece of insulation, and we're taking the ratio of the 10-minute resistance divided by the 1 minute resistance. That's it. It's very simple. We're going to walk through how to think about it and how to actually do it. So for this example, 100 mega ohms, I just picked a number, 90 mega ohms. So if it was 100 mega ohms at 10 minutes and 90 mega ohms at 1 minute, your polarization index would be 100 divided by 90, or 1.11. Now what does that mean? Well, you go look at the tables for polarization index for your particular industry, or you can go to a website of Megger and pull those tables, and it tells you on a numerical value what is no good, fair, and very good, or good. And so you got those numerical values that tell you something. We're probably going to zoom in quickly and show you what those look like from the Megger perspective. But what is this telling you, right? Why do we keep it on for 10 minutes? And what is happening with the insulation, and why does it mean anything? Well, what we're doing, we're putting some electrodes on either side of a piece of insulation. So let's say this is insulation material right here, and here are your electrodes from your insulation resistance tester, and you're just hitting it with a big voltage. Well, what's going to happen is the molecules of the insulating material are going to begin to orient opposites attract and like repel, in electricity. So on the positive electrode, the molecules are going to want to align the negative side of the molecule with the positive electrode. And so you're going to have a twisting of the molecules as time goes on in the polarization index exercise. So initially, when you hit it with this high voltage, 5 kV, 10 kV, or 15 kV, the molecules start turning, all right, to orient. Opposites attract and like repel. So, for example, if you have a molecule where the negative is aligned to the positive electrode and the positive is aligned to the negative electrode, well, this molecule won't want to spin at all, right? Because he's already in line with the opposite, and there's nowhere to turn because he's already perfectly aligned. However, consider a molecule like this particular molecule where the positive and the negative are not quite aligned with the positive and negative electrodes, right? So this molecule is going to want to probably spin this way and rotate to where the negative is lined up with the positive and the positive is lined up with the negative electrode. Similar fashion, let's just another example. Consider this molecule, which is completely out of alignment because positive and positive repels and negative repel. So this molecule is going to want to spin to get into alignment. So let's consider he might spin that way, right? Maybe. He might spin the other way, but he's going to want to spin. So, and again, this particular molecule, now your imagination is probably tuned in to how this works. So the positive and the negative molecule portions of it, it's going to be rotating in this direction for this particular molecule. So that's polarization index. And what is it telling you? Well, when you consider a material that's new, say a new insulation, it's kind of rubbery, so you can kind of intuitively think the molecules are going to be easy to move around, right, and realign, right? Okay, that molecule is going to move, easy to realign, easy to move. If it's dry rotted, i.e. bad insulation, it's going to be stuck and it won't move much. So as time goes on, there won't be much change in resistance because it's dry rotted and the molecules are stuck, right? So that's an intuitive way to think of it. A stuck molecule versus a molecule that can move around that's rubbery. Dry rotted versus not dry rotted. That's a good way to think of it. Another way to think of it is if you've tested motors before, whenever you first test the motor and you turn it on and you have a current meter, well, there's a big inrush current where the current is high when you turn the motor on, and as it catches speed in this freewheeling motor, the current goes down as it approaches its top speed. You can kind of think of that here, where you have a large current when you first start a polarization index. All right, large current means smaller resistance if you look at the R equals VI equation, and as it gets to its equilibrium point, the current goes down, similar to a motor, right? Once it reaches its freewheeling steady state, you get a smaller current. And if you got a small current, you have a larger resistance. So if you look at the graph here, that's kind of sort of what you expect to see as the polarization procedure starts off in time at a lower resistance and slowly go into a higher resistance. So the slope of this curve tells you the polarization index. So we're going to go and actually look at a specific case where I pulled an extension cord out of my garage, and I'm going to perform a polarization index. I'm going to take some snapshots with this camera. So as I perform the test in my extension cord that I found in the garage, I'm going to show you what I'm going to do on the board, and then we're going to go out and look at the instrument and how to set it up and quickly do a polarization index test. So I got a typical American style plug here. So what I'm going to do is I'm going to test the insulation of the neutral against the insulation of the cord, and we're going to just basically put the electrode around the insulation, one electrode around the insulation, the other electrode on the neutral, and we're going to perform a polarization index test with that quick setup. So if you guys have test equipment and you basically want to do it today to figure out how to get this stuff done, or how to do it, you know, quickly, you just go grab an extension cord out of your garage and you can practice and do a couple of tests, and then you know how to do it after that. Alright guys, we're going to do a polarization index test with this particular instrument here, the Megger S1568. It's a 5 kV insulation tester, or 5,000 volts. So the setup, as I said on the board here earlier, is an American style cord. We're going to test the insulation resistance between the neutral here and the insulation. So if you look at my test setup here, basically, like I said, I got a extension cord out of my garage. So I put one of the electrodes on the insulation directly here. See that? And then I put the other electrode on the neutral. Very simple setup, right? So let's go to the instrument and do the settings, and then hit go, and then we'll get it started here. And there's IR here, insulation resistance, and basically you want to move it to the PI, polarization index. All right, so let's move that guy to PI. We have our setup here on our extension cord insulation. We stabbed in our leads, and we just need to crank up the voltage on this level here, and then start our polarization index test. Okay, let's just go 5,000 volts. I like to bring instruments to their limit sometimes. All right, so I guess we're ready, and if you can see the screen, just watch as I start it, and then we'll cut away for waiting, and then come back. All right, let's start it. Okay, I'm going to zoom in on the screen here a bit. So you can see at the bottom the timing. It's taking note of the timing. So you see the voltage level it's at now, 5106. You see the current leakage around 50 somewhat nanoamps. And it's taking the equation there to give you the giga ohms. But you see we're at the 28, 29, 30 second mark. So it's gonna, when it gets to the 1 minute mark, it's gonna capture the insulation resistance, and then it's gonna hold it, and then wait till the 10-minute mark and capture the insulation resistance there, and then you're gonna see the polarization index display on the screen. So we'll cut away here so you guys are not waiting. All right, guys, we're almost to the end of our polarization index test here. You see at the bottom left the minutes and seconds left. So remember, it's a 10-minute test, and so In a few seconds it should be done, and we'll look for the polarization index on the screen. All right, and our polarization index is 1.23. See that? 10 minutes is done. Polarization index 1.23. The insulation resistance ended at about 129.6 gigaohms at 39.4 nanoamps. So you want some sources on what all this polarization index does, go to the Mega website and get this file, a guide to diagnostic insulation testing above 1 kV. Download the file, and I'm going to show you where to go inside to understand what the polarization index numbers mean specifically. And you see within page 17 of this document, it starts getting into some of the graphs of the polarization index and how to think about it and what it should be doing. And then you scroll down slightly from here. Right here you see the graph of what each number means. So once you get the number, you come to this particular table and you figure out whether your insulation is poor, questionable, okay, or good. And that's pretty much it.